So, this is actually a more likely kind of problem that you might see on an AP exam question. So on their syllabus, they have that students must know how to do a left-hand Riemann sum, a right-hand Riemann sum, and a midpoint Riemann sum. And we'll talk about later what's known as a trapezoidal rule sum. So it's a way of approximating a definite integral, which is what this thing is there. And so it's by using rectangles to approximate the area of the curve. So if we're doing a left Riemann sum, then what we have, I'll give you a visual, but you don't have to have this actual picture that goes with it. So whatever this function looks like, when x is 1, y is 15, so we only know a few select values of the function. When x is 3, then the value of the function is going to be 8. And when x is 5, then, oh, I didn't really want to make those evenly spaced. I did, so we'll go ahead with it. So when x is 5, then the y value is 5 as well. So we know the function at a few select values, and in general, we don't know anything else about it. So you can't assume, that it's always going to be, coming down in a nice predictable way, except that I did say that the function is always decreasing. So with that information, that's going to help us to answer part C here. Without that information, we couldn't, because you can't assume, what it's going to do in between two given points, because it could go crazy and do all kinds of stuff. We don't really know that. So whatever our function does, we may be assuming that it does, well, we know it's going to decrease. How it does that, we don't really know. To approximate that area of the curve, first with a left Riemann sum, we're going to take these rectangles where the left side of that delta x, or that width, or that subinterval is what's going to go into the function for the height. And likewise for this one. And so it means we're going to get only 2 rectangles. So what we would do then for a left Riemann sum is we're going to say that this integral from 1 to 5 of f of x dx is going to be approximated by, and we're just going to take the base times the height, which notice the base is going to be the left side. So here's the two sides of our subinterval. That's the beginning and end of our first rectangle. So we're taking the one on the left side, that's the y value 15, times the delta x, which is the difference between these x values. That's going to be the 3 minus 1. And so that is going to be 2. And then the next rectangle is going to be this rectangle, which we can see, there's a visual, but you don't have to draw a picture. You can see that between these two, the beginning and end of that interval, the left side is going to give us the height. That's going to be the 8. And the width is going to be the delta x, which is 5 minus 3, which in this case is going to be 2. And so then we just do the arithmetic. So 30 and 16 is going to be 46, and that's our approximation. See how we came up with that? I'm going to push this down a little bit. Still learning. Otherwise, it's going to have a nice view of the picture. Okay, so then on the right Riemann sum, now we're going to make our rectangles using the right side. So on that first one, this is going to be the rectangle, and on the next one, this is going to be the rectangle. But again, you don't have to draw the picture. You can get it from here. If again you see, here's the first rectangle, but now we're going to use the right side of that rectangle, that height, as the height of our rectangle. And so this is going to be approximated by 8. And again, the delta x is 3 minus 1 is still 2. So that one is going to be 8 times 2. The second rectangle here, we're going to use that right side as the height. So that's going to use the 5. And the delta x is again 5 minus 3 is going to be 2. And so here we're getting 16 plus 10 is 26 is going to be our approximation. Now, what we want to be able to see too, now to answer the third question, is the approximation an over or an underestimate? We can see, hopefully from the picture, that because this curve was decreasing, now it's not the concavity that matters here, but the fact that it's decreasing means that our left rectangles are gonna have a bunch of an overcount. We're overlapping a whole bunch. So we would say that the left Riemann sum is going to be an overestimate. So this is going to be an overestimate. And it asks why, and so it may sometimes on an AP question say justify. And so the reason that's an overestimate for a left Riemann sum is because F is decreasing. That would be your justification or explanation. Don't say anything about concavity because you're answering a different question. And it seems like it's maybe silly right now, but later on when we talk about a trapezoidal rule for approximating the area using trapezoids, then it's the concavity that matters, not the increasing and decreasing. And so your answer for a justification, which is a pretty regularly occurring AP question, is gonna have to do with increasing, decreasing for rectangles, but concavity for trapezoids. And sometimes people don't know, and so they're not sure, and so they kind of shotgun it and try to throw it both out there and say, oh, it's gonna be an overestimate because it's decreasing and concave up or whatever, and then you've lost the point because when you introduce the one that doesn't matter, it means you don't know what's going on. So don't try that strategy, it's been tried before. So in this case then we would say, so our right rectangles you can see are leaving gaps in here uncounted. And so it's going to be an underestimate. And the reason again is for a right Riemann sum is because F is decreasing. That make sense? Okay. So let me give you another one. I'm going to give you one here so I can ask you a midpoint Riemann sum. And so I'm going to say x, f of x. And let's see, we can go with, let's go 0, 1, and let me make it different than an increment of 1. So let me go 0, 3, 6, 9, 12. Make sure I have the right number. And so I'm going to just pick some random numbers, -2, we'll say 3, 7, 4, and we'll go with 1. So here now is our, all that we know about this function, all the values of x and f of x. And we are going to approximate the integral from 0 to 12 of f of x dx using a midpoint Riemann sum. And I'll even tell you with the number of rectangles equal to 2. And that's about all we can really actually do. You can give it a shot. Collaboration is encouraged. progress, or do we need help? So if you're making progress, just keep working. If you need some help, I'll try to go through it here a little bit. So how you divide the rectangles up with a midpoint Riemann sum is a little different than what we do with a left Riemann sum and a right Riemann sum. Because what we need to know is really, it's gonna take 3 of these values in the table to make one rectangle. Because we need to know, and they, at least between these 3, they need to be evenly spaced, because we need for that to be the midpoint. That's the midpoint value that we need. So we couldn't just go from 0 to 3 as a rectangle, because to use the value of f halfway in between there would mean we would need to know what is the value of the function at 1.5, and we don't. So we have to group them together so that from 0 to 6 is our one rectangle. The halfway point is gonna be that value at 3, and so our rectangle is going to look something like that. So we're gonna be finding the area of that rectangle using the height of the rectangle at its midpoint for the height of the rectangle, and then the base is gonna then be the delta x, which is gonna go from 0 to 6. Does that make sense? So different strategy than we did in the left and right Riemann sum. So we're gonna say this integral from 0 to 12 of f of x dx is gonna be approximated by, so the height of our rectangle is gonna be that y value at 3, which is 3, times our delta x, which is gonna be that 6 minus 0. So that's gonna be 3 times 6 for the first rectangle. Now the second rectangle is gonna start where the first one ended. So our second rectangle visually is gonna go from 6 to 12. We're in here, or you can see it on the table. We're recycling this 6 as the edge of that second rectangle. So we're gonna need to know the value of the function at the halfway point, which is gonna be the value of the function at 9. That's gonna be the height of our rectangle, and so we are going to get a rectangle that looks like this. Make sense where we're getting those from? And so then we're going to get that height, which is our y value, comes from the table, and then the width is gonna be that delta x, or the 12 minus 6, and so we're going to get the 4 times 6. So our approximation is gonna be 18 plus 24, which I guess is 42, and that's gonna be our approximation to that definite interval. Does that make sense? So the midpoint Riemann sums are a little bit different. They're kind of an animal in their own right, different from the left and right Riemann sums. Okay, questions on any of that so far? So am I right? I think Tim has finished, you've completed the whole worksheet. Is that right?
I think so.
Okay, did you want a hard copy?
Sure.
So you did the ones on the number 2 with the 3 x and all that.
Yeah.
So I think you're ahead of everybody else. What's that?
I tried.
Okay, you tried. So are you okay with it if we try to go through that one? Because I'm trying to get where we can, I don't wanna make you be bored to tears. But so we went through on the video on the in-class stuff yesterday, we went through most of the first problem there as an example. On the video that is on the support materials, it goes through the whole thing. Well, I think, I don't, did I go through the second? I don't think I did. So I don't think the second. I didn't. So it would be worthwhile for anybody, even the people watching later, if we went through number 2. So let's do that, because then I feel like that would be maybe useful for everybody. So we're going to look, we'll see how far we can get. So on number 2, we have a new function. So our function is going to be f of x now is equal to 3 to the x. And our interval now is different than we did on number 1. It's going from -1 to 3, so it's a little longer interval. And first, what we're gonna do is, we're going to find with our, what she calls L sub 8. That's a left Riemann sum using 8 rectangles to approximate the area under the curve, to approximate this integral from -1 to 8 of 3 to the x dx. So that symbolically is what we're approximating. And we know that we have, maybe we don't, 3 to the x is gonna be this exponential growth function. So at -1, this thing is going to be 3 to the -1, which is 1/3, so that's gonna be pretty small. And then by the time we get to 3, this is gonna be 3 to the 3rd is 27, so we'll go 1, 2, 3. Not really gonna try to get this to scale, I don't think we're gonna need it. But it's gonna be an exponential growth function, so it's looking something like that. So that is our function, f of x equals 3 to the x. This is our interval going from -1 to 3. So what we are going to do first is we're going to, so this is the interval, we're going to subdivide that into 8 rectangles. So 8 of these subintervals, we'll call them. So each of those is going to have a width of how much? Each of those will have a width of 0.5, right? So this interval, b minus a, 3 minus -1 is 4. We're dividing that into 8 subintervals of equal width to start with, and so we're gonna mix it up. So each of those is now going to have a width of 0.5. So our delta x, which if we have uniform width rectangles, is gonna always be b minus a over n, the ending point minus the beginning point divided by the number of rectangles. In our case, that's 3 minus the -1 over 8 is gonna give us 1/2. So we have our delta x is 1/2 or 0.5. Now, go ahead and draw this on there. We're gonna first mark up, we're gonna do a left Riemann sum. So let's draw some of those rectangles. So that first rectangle is gonna have the left side of the subinterval, its height, its value of the function is gonna be our height. So it's gonna be right there. There's our first rectangle. And then our second rectangle will come up to the curve and we'll go over to the y-axis because there's going over 0.5. And our third rectangle and fourth, and we'll do this so that we can get all of those 8 rectangles in there. Okay? So what we want is to do this approximation. We're gonna say our approximation is gonna be f of x of 1 times delta x plus f of x of 2 times delta x out to, and we're gonna get f of x of 8 times delta x. So we're gonna plug in these different values of x into our function to get the height of each of the rectangles. Each of the rectangles is gonna have the same width, their uniform width, and that's gonna be our 0.5. So for the first one, since we're plugging in the left end, this is gonna be f of, what is that x value there?
-1.
-1, good. And the delta x is gonna be 0.5. Does that make sense where that's coming from? And the second rectangle, we're gonna plug into that f of -1/2. I'm gonna call it -0.5, that's exactly right, times its delta x, which is 0.5. Now I'm gonna go just ... out to that very last rectangle, our 8th rectangle out here. What is the x value that we're going to plug into that?
2.5?
2.5, right? It's 0.5 left of where we're gonna end up at 3. So that's gonna be an f of 2.5 times our delta x, which is 0.5. So here is where we're going to figure out how to use our calculator to make this arithmetic more manageable. So in a moment, we're gonna go to our calculator, and what we're gonna put into list one is gonna be all of these values of x that are going into our function. There's gonna be 8 of them, because we have 8 rectangles. The first one is -1, then a -0.5, then we're just gonna keep going up by 0.5 each time. So we're going to get to there, okay? So we can grab our calculator, and we can go to stat, and then hit enter. And if yours is like mine, it's got a bunch of junk in those. I've got mine filled in all the way to L4 because I was doing this yesterday. So whatever is in, whatever lists that you have with data, we're gonna clear that out. So if you go up arrow into what's called the formula bar, hit clear and enter, it's gonna wipe the slate clean. Is anybody not seeing L1? Because sometimes if it gets goofed up, you may not, we can get you to see that. So everybody sees an L1. Okay, it's all clear stuff, so now we're gonna enter these into L1. So it's just kind of tedious, but you go -1, enter, -0.5, 0, 0.5, 1, 1.5, 2, 2.5. So you should have 8 entered into there. Okay. Now, in the next column, in our L2 column, what we're gonna do is we're gonna plug all of those values of x that we put into L1, we're gonna plug it into our function 3 to the x. And that's gonna give us these values right here, these heights of our rectangle. So to do that, we're going to go up arrow, or first right arrow into L2, then go up arrow into the formula bar, and then what you're gonna type in there is just 3 raised to the L1 power. So in there, you're gonna go 3 raised to the, and then go second 1, and it's gonna look like 3 to the L1. So that's telling the calculator to just plug in all these values one at a time in there. So when you hit enter, it should populate all of L2 with 3 to the -1, 3 to the -0.5, so on. So you should see like 0.33333 in the first entry right here, because that's our 1/3, and then whatever it is, 0.57735, and on and on and on. So there's something in all of those, okay? So then we're gonna go to L3, and L3, we're gonna put in our delta x. So that's gonna be what we're gonna multiply each of these by for the width of our rectangle. Now ours right now is all 0.5, but hopefully if we can get far enough, we're going to do a variable width Riemann sum, in which case that will be something different. So just go right arrow and just hit 0.5 and enter repeatedly until you get all of those filled up. So then we will go to L4, and so in list 4, so we can right arrow into list 4, and what we want to do now is take our heights, which are in L2, those are the f ofs, so that's the height of a rectangle, times the delta x, which is in L3, and that multiplication will be the area of each of those 8 rectangles. So we're going to up arrow again into the formula bar, and we're going to type in L2 times L3. And so once you're up there, you're going to go second, the 2 button, times second, the 3 button. So there's L2 times L3, and when you hit enter, it's going to fill that all in. And I think I'm getting like 1.16667 or something like that in the first one, so we can see if we're agreeing on all of that. Is that okay? So now that, right now, what we see in L4 is the 8 rectangles that we're trying to add up. So now we have to get out of the tables part. So we're gonna go second mode. That's gonna take us back to what's called the home screen. And now we want to add all of those up. So if we go second stats, that's the list menu, and arrow twice to the right, then option number 5 is that sum. And so we want to take the sum, so hit enter there, so go to the sum, hit enter, and we're gonna put in L4, which is second 4, and it will add all of those up, and I'm getting 18.214 rounded to 3 decimal places. Is anybody not seeing that? Okay. So, armed with that, we can do a right Lima sum, which you would just have to, instead of using this as your first value, because we wouldn't use this value for a right Lima sum, but we would at the end use that one. Does that make sense? So you can doctor that up and do it. Now, every time you do it, you're gonna have to, anytime you change something in here, you're gonna have to go into the formula bar and retype in 3 to the L1 power so that it'll recompute them. Because even though you change something here, it won't automatically change the stuff over here. You have to redo the formula each time. Okay, so I wanna move to the harder one. So I'm gonna go to where we're gonna do a variable width, let me see if we can do a variable width, variable height rectangle. So this is the part C now, okay? So we're going to, let me redraw this here. Because this, I think, is the hardest one, but if we do it together, then we have some idea of what we're trying to do. So we again have, we're going from -1 to 3, and we have, our curve is looking something like this. Now, we're going to, because we want 8 rectangles in between here, to create 8 spaces, we need to make 7 tick marks. But we're going to make these be variable width, so we're not gonna make them all 1/2 like we did before. So we're gonna go around the room here, and so what I'm gonna ask you, starting with Gavin, is I want you to pick a number, and we're gonna keep it a little simpler, so you could be as creative as you want, but we're just gonna go to 1 decimal place. So when I ask you for a number, I don't want you to say 1.87659, it's too big a headache and we don't have unlimited time. So I'm gonna ask you for something that's gonna have just something point something. Okay, does that make sense? Now remember, save enough space, because since we're getting 8 rectangles, we gotta get 7 squeezed in here between -1 and 1. Okay, so pick a number.
-0.8.
Minus 0.8?
Yep.
So our first one right here is gonna be a very narrow one. So I'm gonna write down the -0.8. Okay, and Garrett, now you can pick anything between -0.8 and 3.
+0.1.
Positive 0.1. So we're gonna be here, it's gonna be positive 0.1 is our next one. And Miranda, now you get to pick anything between positive 0.1 and 3. 0.2. Okay, we're gonna get some really big rectangles here in a little bit because these are very small. Evan, pick a number between so far you got 1, 2, 3. We have a total of 7, so you can pick a number.
0.8.
0.8. So that's gonna be 0.8. So you got 1, 2, 3, 4. Okay, it's to you, Tim.
1.6.
1.6. So we have 1, 2, 3, 4, 5. We got 2 more to go. To you, Gavin, anything between 1.6 and 3?
2.
2. And so I think we're up to the last one. 1, 2, 3, 4, 5, 6. So Garrett, anything between 2 and 3?
2.7.
2.7. Okay, now, we're going to fill in our delta x's, first of all, because that's what we know so far. So to get our delta x's, we're going to have to,
Which problem is this?
this is I think we're at part C.
Okay.
So this is part C that we're doing, part C. So the first delta x is gonna be this width of that first subinterval, which is going from -1 to -0.8. So if we take the right minus the left, a -0.8 minus a -1 is gonna be, waiting for it,
Negative point nine,
Point two.
or negative point seven.
Wait, what? What's the question?
Is it
Point one or one?
-0.8 minus a
So
-1.
1.8.
Point two, yeah.
0.2.
Point, what? Okay.
So it's like -0.8 and a 1.0.
Oh,
It's gonna be a 0.2 for a width. Okay, I'm gonna do this as we go. So I'm gonna go to stats, enter, right arrow, let's see, I go to L3, and I'm gonna, L3 is our delta x's, I'm gonna up arrow, go clear, enter. So we're gonna put in 0.2, we said for the first one. Now the second one, we wanna go from -0.8 to +0.1. What's that delta x?
Point nine.
point
What
seven.
would you say?
Sorry, I wasn't counting on this being the hardest part. -0.8 to +0.1, what's that distance?
Point nine.
Point seven.
So, oh, you're right, I was doing it wrong. You're right, it is 0.9, it is 0.9, I was thinking. Gosh, you guys had it right. That's what the part that was surprising me. After that last one. 0.1 to 0.2, what's that gonna be?
Point one.
There we go, we can do that one.
Too scared to answer.
I know. You get called out. 0.2 to 0.8, that's gonna be
Point six.
0.6. And 1.6, 0.8 to 1.6, 0.8. And 1.6 to 2, that's gonna be
Point four.
0.4. And what do we go, 2 to 2.7, what's that gonna be?
Point seven.
And finally, the 2.7 to 3, that's gonna be,
Point three.
okay, I gotta answer those real quick. Now, we're gonna be thinking, we're gonna go around again, and what we're gonna do is we're gonna pick numbers in each of these subintervals to plug into the function to get the height. So here we've got the random width, the variable width, and now we're gonna pick variable heights. So we're not gonna do the same thing each time. Let me get caught up, so I got 0.2, 0.9, 0.1, 0.6, 0.8, 0.4, 0.7, and 0.3. Okay, so we can arrow over to L1, and let's clear that out. So you can go up arrow, whoops, up into the formula bar, hit clear and enter. So now what we're gonna do is, we're going to pick a number on this subinterval that we're gonna plug into the function to get the height. We're gonna enter those into list one. So where do we leave off? I think Garrett got the last call, so Miranda, you can pick any number you want between -0.1 and -0.8, including -0.1 and -0.8. -0.9, you write those down here. So that's gonna be a negative, I did that, so we go -0.9. So I'm gonna enter that -0.9, oops, 0.9. Okay, now the next one, we wanna pick a number between -0.8 and +0.1. So Evan, that's your call, -0.8 to +0.1.
Negative point three.
-0.3 will work. So we're gonna plug in a -3. And now we want something between -0.1 and -0.2, and I think we're to 10.
Could we just do point two?
We can, -0.2, or +0.2. +0.2, you can use an endpoint. Oops. And now we're between 0.2 and 0.8, so back to Gavin,
Point five.
0.5. And now we're between 0.8 and 1.6, Garrett,
1.2.
Miranda?
1.9.
1.9. And between 2 and 2.7?
2.5.
2.5? And between 2.7 and 3, back to you, Tim, for the last one?
2.8.
2.8? Okay, does it make sense what we're doing here? So we have these rectangles of various widths, they're variable width. We're picking just random points in between there to use as height. So it's variable width, variable height, Riemann sum rectangles. So now we're gonna do like we did before. We're going to evaluate the function at these points that we picked and put into L1. So we're gonna go right arrow and up arrow into the formula bar again. And we're gonna have to retype in that 3 raised to the L1 power. So 3 raised to the second one and hit enter, and it recomputes those. My first one is like 0.37204. And then it's got other stuff going down. You okay with that? Now, we already put in our delta x's as we chose those from before. So now we're gonna go arrow over to L4, up into the formula bar, and again, we're gonna say L2 times L3. So second 2 times second 3, hit enter. And my first one is like a 0.07441, does that sound right? So 0.0707441, and it's got various things going down. So remember, these each are the areas of those individual rectangles that we created as we found the heights and widths of those various rectangles. And so now what we're gonna do is we're gonna add them all up. So we'll go second mode, back to the home screen. And again, we're gonna do the sum, which is second stat. Right arrow twice to the math menu, down to option 5 is sum of L4, which is second 4. Anybody else getting 25.515? Okay? So you still have more to do because you have to do a right Riemann sum, a midpoint Riemann sum, and a uniform width variable height Riemann sum. So at the bottom of the page, I think it's at the bottom of yours. So it asks for a symbolic representation of that. So a definite integral is simply the limit of a Riemann sum as the width of the interval gets smaller and smaller, as indicated by that formula. The limit is delta x goes to 0 of that. So then it tells you this kind of interesting, the FN integrate option on your calculator uses Riemann sums, but with delta x that's 1/10,000, is 1/10,000. So it adds up a lot of rectangles to get an approximation. So with that integral from 0 to 2 of x squared, draw a quick sketch and use your calculator to make sure you have those calculators good. Do you know the 2 ways to do this? If I can get it in, I did this last time, I think, too. So can you do FN integrate?
Yeah.
So that's the most important. Go math. Option number, I think, 9 is FN integrate. If you have a new calculator, you're gonna just go from 0, up arrow to 2, and you can right arrow and plug in x squared, and then right arrow to dx, hit enter, and you should be getting 2.667. If you have an old one, you're gonna put in first the function, so go x squared. And you could have just used that x2, comma, comma, and then the x, because you're integrating with respect to x, comma, lower limit 0, comma, upper limit 2, and the parentheses, and the What's that?
Should have been 2.66.
And then, and when you get to the third decimal place, it should round. It's 2.6666666. Yeah, and if you round to 3 decimal places, and we would round, you know, it would be 2.667. I mean, you could do more always, but you have to at least 3 AP.